This is chapter 16, RCL and tuned circuits. These are questions in experiment only. And a summary for the chapter. If you haven't read the chapter, go ahead and do so and make sure you study and understand all of the concept in it before you complete this presentation. Number one, networks are AC circuits that have resistors, capacitors, and inductors placed in the circuit to pass, reject, or to control current. Number two is resonant frequency in a circuit occurs when the inductive reactance, or XL, is equal to the capacitive reactance, or XC. 3. The formula for frequency is resonance. And again, 3, the formula for frequency of resonance is, as shown at the top right, FO equals to 1 divided by 2 pi, and then the square root of LC. And it can be further simplified to FO equals to 0.159 divided by the square root of LC. Again, L is the inductance, C is the capacitance. 4. In a series resonant circuit, the current is maximum and the impedance is minimum at the resonant frequency. 5. The series resonant circuits pass currents at resonant frequency. 6. Tank circuits oscillate, providing an AC signal at a desired frequency. 7. In a parallel resonant circuit, the current is minimum and the impedance is maximum at the resonant frequency. 8. Parallel resonant circuits reject currents at resonant frequency. 9. The Q of a circuit describes the relationship between XL and R. Again, that's inductive reactance and resistance. And the formula for this is Q equals XL, or inductive reactance, divided by resistance. 10. The 4 types of filtering circuits are low pass filter, high pass filter, band pass filter, and band reject filter. 11. A nomograph is a chart that can be used to solve problems involving inductive reactance or capacitive reactance and resonance. And I will show you an example at the end of this presentation of a nomograph and how it could be used. Review questions. Review questions for section 16.1. Resonant frequency is a special condition of RCL circuits in which inductive reactance is equal to capacitive reactance. 2. Find the resonant frequency using the values given in the following circuit. And this is the circuit. We have a 5 Henry coil or inductor. We have a 0.1 microfarad capacitor in line, all in series with an AC source. And we have the resonant frequency formula up the top right. FO equals to 0.159 divided by the square root of inductance and capacitance times capacitance. And we have the inductance and capacitance. We plug those in, which is 5 million. Remember, we have to make them into similar or equal units. In this case, we're going to go with micro. So we're going to turn 5 henries into microhenries, and that is 5 million. 5 million microhenries equals to 5 henries. So we plug 5 million in times 0.1, which is already in micros, 4 microfarad. We get 50,000 megahertz for our resonant frequency. Number 3, in a series resonant circuit, the impedance is N or A, and the answer is at a minimum. Number 4, periodic current changes in a tank circuit are described as a flywheel action. Number 5, in a parallel tuned circuit, the circuit is a reject, or the circuit rejects currents at the resonant frequency. Number 6, the relationship between the inductive reactance and resistance in a circuit is stated by the Q of the circuit. What causes the tank circuit to stop oscillating? That is eventually, and that is the resistive factor of the circuits. Jumping on to review questions for section 16.2. Again, if you haven't read the chapter, go ahead and do so. Fine for doing these. Attenuation. There is no point of doing these without understanding every concept of the chapter. Number 1, attenuation. These are for reference. When a signal, just to check amplitude or intensity is decreased. These on your own, and look back into the chapter where a question still remains. Number 1, circuits or separate specific frequencies. Circuits that separate specific frequencies are called filters. 2, a capacitor will pass AC and block DC. 3, a low pass filter. In a low pass filter, high frequencies are rejected. 4, when a series resonant circuit is used as a band pass filter, it accepts only currents near its resonant frequency. Number 5, what is a nomograph? It is a series of charts that allow finding inductive reactance, capacitive reactance, and resonant frequency or capacitance. If two of the 3 values are known by aligning the values that are known with a straight edge. Again, I will show you the nomograph at the end of this chapter. And these are the test your knowledge questions. These are the chapter end questions. Number 1, what is the formula for resonance? And you can see a version of it right following the question, which is 1 divided by 2 times pi times the square root of inductance and capacitance. A shortened version of it is 0.159 divided by the square root of inductance times capacitance. Number 2, compute the resonant frequency for the following. And although you can see the answers right next to each of the sections, A, B, and C, there on the right side of the screen is how you work out each of those problems. I won't go all the way through these, as you can probably most likely see those and work those out, and you are probably just verifying, make sure that your problems or that your method is correct. These are my methods, and I got those answers using these methods, this method, and I got that directly from the text, so they're probably most likely correct. And just to go through one of them, so I can go explain a few of the nuances of the solving of this problem. You have to basically just plug in, make sure that your units are equal. For this, in this case, instead of going with a whole bunch of zeros because we're dealing with picofarads, we're dealing with microfarads, we're dealing with many zeros, in some cases probably more than 9 zeros. So we're going to go with the engineering notation or scientific notation method, and we basically transform each of the units, whether it's micro or pico, into scientific notation. In this case, we have 100 microhenries, which could be written as 100 times 10 to the negative 6. And you have to multiply that. That's at the bottom of the equation there, of the fraction on the right side of the formula of the equation. And we have that multiplied by 250 times. Again, we're dealing with a pico, so it's times 10 to the negative 9. We can simplify that further. We multiply the two numbers that are just plain whole numbers, 100 and 250. We multiply that, we get 25,000, and we're left with times 10. And to multiply the 10 to the negative 6 by the 10 to the negative 9th, we have to add their powers. Negative 6 plus negative 9, we get negative 15. So we get 10 to the negative 15th power. And remember, I made this mistake once. Remember to carry down your square root symbol. That has not gone away. So next, we're still on top of the screen. 0.159 divided by the square root of 25. The square root of 25 times 10 to the negative 12. And why do we do this? If you want to focus again on the top right, where we have the square root of at the bottom of the fraction, square root of 25 times 10 to the negative 3 times 10 to the negative 15. Why do we get that? And that is because we went from 25,000 to 25. So we're taking away 3 zeros, so we're basically having to make that up. So we do that by putting this or writing this into the scientific notation again. So 25 times 10 to the third is the same as 25,000. So we put that in that format. That way we can further simplify the 10 to the negative 15th power. And we are left with 0.159 divided by the square root of 25 times 10 to the negative 12 power. We solve for the square roots, and we're left with a quick way to do that is just inverting your power. So we are left with 12.5 times 10 to the 6 instead of 10 to the negative 6. We're left with 12.5 times 10 to the positive 6, or just plainly 6. And we go ahead and divide 1.59 divided by 12.5. We get 0.013. And we still have the multiplication 10 times 10 to the 6. And we are left with we're left with 13,000, and that is in hertz, and we can call that 13 kilohertz, and that is the answer. And you take the same steps to solve for the rest or the other two problems. 3. A series resonant circuit is sometimes called a or an acceptor circuit. 4. Explain the flywheel action of a tank circuit. The way this works is I'm going to help explain this, I'm going to include a graphic. But basically, you have a switch in line with a parallel capacitor and a inductor. They're both in parallel, and there is a switch in between them also, so there's two switches in this circuit. When you first close the switch, in this case switch 1, which is the one closest to the power source, and open up switch 2, you charge your capacitor. Your capacitor is charged to the same level as the source, so it's basically it becomes charged as much as the source. If it's 5, 4, 12 volts, however many volts it is, that's how many volts your capacitor is going to have. Current stops flowing once the capacitor charges because the circuit is in balance with the power source, so current stops flowing. And then in step 2, we open up the switch for the source. Basically, we take the source out of the equation, and we close switch 2, where basically your capacitor is connected to your inductor, and they are in parallel. They're right next to each other, right across from each other. So once we close this switch in between them, the capacitor, the first thing it's going to do is discharge. It's going to discharge in the opposite direction of the flow of the power source. The flow of current will flow opposite from what the power source flowed just earlier when the other switch was closed, and it will charge the inductor. There will be a magnetic field expand while the inductor is charging, and current will flow in the same direction as the capacitor just provided the currents. So basically it will charge the capacitor on one side while the current is flowing on the top side, as you can see. And once this is done, once the capacitor and the inductor are both in balance, they're both charged to the same level, then there will be no magnetic field expansion at the inductor. Therefore, current will stop flowing. But guess what? When current stops flowing, then the capacitor will again try to discharge in the opposite direction. And once again, if you discharge in the opposite direction, then the current, then the magnetic field will collapse, will be in the opposite direction, and again, current will flow, will be helped out by the inductor once again, and this will charge the capacitor in the opposite polarity. And this cycle repeats itself over and over, so you get something of an AC current flowing within the circuit of the capacitor and the inductor. Question number 5. A parallel tuned circuit is sometimes called a or an reject circuit. Question number 6. At resonance in a parallel tuned circuit, the line current is minimum or at minimum. Number 7. State the formula for determining the Q of a circuit, and that is Q equals to inductive reactance divided by resistance. Number 8. A filter is a circuit that separates specific currencies. Number 4. Name 4 general types of filters, and that is low pass filter, high pass filter, band pass filter, and band reject filter. Distinguish between high pass and low pass filters. High pass filters reject lower frequencies and currents, and low pass filters reject higher frequencies and currents. And as I told you, this is the nomograph. And just to read here, the nomograph or alignment chart shown in this figure shows a rapid and handy method for solving problems involving inductive and capacitive reactance and resonance. To use this nomograph, you need any two variables involved in finding resonance. The chart has lines for L, C, and XC, and FO. And to find the missing value, line a straight edge across two variables that are known. Then see where the straight edge crosses everywhere else on the chart. The following will aid you in using and understanding this chart. The examples are there, number 1, 2, and 3. And just to go through number 1, what is the reactance of 0.01 microfarad capacitor at 10 kilohertz? And for this, you use the upper chart, place the ruler or straight edge at the 10 kilohertz on the frequency scale and 0.01 on the capacitance scale. The rule crosses the reactance scale approximately at 1600 ohms, and that is the case. You can zoom in and see that line crossing the 1600 ohms. I know it's a bit fuzzy, but you can see this chart on the text or look for one, download one from the internet. Experiment 16-1, demonstrate RC coupling. During this experiment, you will demonstrate RC coupling. You will construct a circuit upon which the DC component of the incoming signal appears across the capacitor, and the AC component appears across the resistor. This important principle will be discussed in more detail in later chapters. The materials needed are one 10-volt DC power supply, one variable AC power supply, one microfarad capacitor, one 24 kilo ohm resistor, and a multimeter. Step 1 is to examine the circuit shown in Exhibit 16-1A. 2. Compute the reactance of C as follows. See the formula. And the reactance is 2650 ohms, 2650 ohms. Resistance should equal 10 times the capacitive reactance, or 26,500 ohms. A 25,000 ohm resistor is suitable for this experiment. Step 3 is to set up the circuit shown in Exhibit 16-1A and set your power supply for 6.3 volts AC at 60 Hertz. Connect the 6.3 volts RMS terminals of a power supply in series with a 10 volt DC supply. Connect the power supplies to the circuit and have your instructor check your circuit before turning on the power supplies. Step 4 is to take several measurements across C with a meter set to read DC volts. Measurements across C with a meter set for DC volts should read 10 volts. Do your readings agree? Number 5. Now measure for AC volts. The meter set for AC placed across the same points should read 0. Do your readings agree? 6. The measure for AC voltages across the resistor R. 6. Next, measure for AC voltages across the resistor R. An AC meter reading across R should read 6.3 volts. Do your readings agree? 7. Measure for DC voltages across the resistor. Do your DC meter reading should show 0. Do your readings agree? Finally, what conclusions can you draw from your results? How do your readings relate to RC coupling? And just an interlude for magnetic resonance imaging, or MRI. A most interesting way to look at the human body is through a process known as MRI, or magnetic resonance imaging. The MRI technique is based on the principles of magnetism and radio wave transmission. Using MRI, physicians are able to identify abnormal tissue without performing surgery, like radiography or fluoroscopy. MRI does not expose the patient to radiation. MRI is safe for most people, but because of the powerful magnets, it cannot be used on people with metal implants such as pacemakers or artificial joints. The patient is placed in a large circular magnet and a magnetic field is applied to the patient's body. The magnetic field causes nuclei in the hydrogen atoms inside of the body to line up. A radio wave is then transmitted through the patient and picked up by a receiver. The frequency of the radio waves set up a resonant condition in the hydrogen atoms. This condition enables the nuclei to absorb the energy of the radio waves. When the radio wave stimulation stops, the atoms return to their original state and emit energy in the form of weak radio signals. The radio signals are then translated by a computer, and the image is constructed based on the intensity of the radio waves interacting with the hydrogen atoms of the patient. Variances in the proportional content of the hydrogen for each organ determines the type of image produced. MRI is typically used to examine the head and spine, but it is also used to examine organs such as the heart and lungs and joints. The detailed cross-sectional images allow physicians to see blood moving through the veins and arteries, to see a swollen joint shrink in response to medication, and to see the reaction of cancerous tumors to treatment. Some machines use the superconductor principle to produce the powerful magnetic field needed for MRI. The magnets in the ring are cooled to extremely low temperatures using liquid nitrogen or liquid helium. Once they have been cooled, electricity can be conducted with little or no measurable resistance. The lack of resistance in the coils is what enables such powerful magnetic fields to be produced. And this is the end of the chapter questions and experiments. Congratulations, you have earned this electronics course rank. Please do look for the next chapter and continue your studies. Thank you very much.